Hello, welcome all of you to the video lecture on fluid mechanics for process engineers. I am R Naren from School of Chemical and Biotechnology, SASTRA. This is the learning capsule, the second learning capsule of module 7, where we are going to see on capillary rise. The suggested readings of the book by Munson and Fox on fluid mechanics, a very standard textbooks rather. Now, what we have seen in the learning capsule 1 is that there is possibility of a flow through capillary which does not requires a pump, but there is certainly a fluid motion can be induced in such small section channels. What I mean by capillary is small cross section channels. So that means this gave rise, this observation across, rather we would say that has been of interest to so many physicists, and this resulted in the famous the Young's Laplace equation, which gives an understanding of what happens in such small cross section channels. Now, as part of this learning capsule, we are not going to see in detail of the Young's Laplace equation, but what I am going to do is to use the principles of the Young's Laplace equation and see whether can we predict a capillary rise. Now, what is the reason for flow through capillary is being investigated. One primary reason is the interaction of the fluid right with that small channel. Now, this is found out, this is something is modeled, rather I would say, as using the concept of surface tension. We observe that a fluid always takes a shape so that it can conserve the surface energy per unit volume basis, and this probably could lead to a reasoning of why there is a flow in the capillary. Now let's take a sketch and then take it further of how we do a capillary rise. Now let's consider a capillary. So this is a capillary, you can see dipped, let's say, in a fluid. Now this fluid rises through this small capillary. Certainly there are forces acting on this, because if this fluid has to rise, initially there won't be any fluid and the fluid then rises, so there should be a force acting on this. Now the question is, what is this force? Can this be a pressure force? Now you can just see this diagram and we can easily understand, see the sketch and easily understand that the pressure force need not be the reason in this case, for the simple reason that this is also open to atmosphere, and the atmosphere or the surrounding acts on this, and if we even dip without immersing it into a longer, so that means it is just very close to the surface, still you see the liquid being pushed. So that means if this is neglected, it is very small, it is just on the surface, this pressure is also equal to the atmospheric pressure, and this pressure here is also equal to atmospheric pressure. We really don't find any pressure difference between the two fluid layers, so the pressure force could not be the reason for this pushing of fluid into this capillary. So at least one force we don't hypothesize to be the reason for this. Obviously gravity must be acting, so the gravity force would be acting, but this is acting down. Let us assume that the Earth's plane is like this and this is the altitude Z, so that means the gravity is acting in this direction, but this gravity force is then on the downward direction, whereas the fluid is expected to go up, so the fluid actually goes up. So that means there needs to be at least one another force, right, that should not only act against the gravity but should be the reason why the fluid gets pushed into the small capillary. Now if we just zoom this part, I have slightly zoomed it increased the size, one can easily observe that there is actually a curvature of the fluid layer. Now this curvature is what is being predicted by the Young's Laplace equation, or using the concept of surface tension that we have seen in the earlier videos. So that means a fluid surface always tries to minimize the surface energy per unit volume. So that means the molecules that are on the free end of the fluid surface are hypothesized or assumed to be in a tension. So that means there is a force that is acting on this fluid surface, and this fluid, when is in contact with a solid material and you have an air, typically I am assuming that this is exposed to atmosphere, so that means there is air here. So that means this surface tension force could be then another force that is acting on this fluid column. So now we have two forces. One is the gravity force and another is the surface tension force. And we see that a fluid rises to a capillary and comes to a stable height. Now if let us mark this height based on the lower meniscus, let's say if this height is h, this is, let's say, the diameter of the capillary tube, right? So that means once the equilibrium point is reached, so that means the gravity force is exactly balanced by the force due to the surface tension. The surface tension force acts at an angle which we call as the contact angle with respect to the material. Let me just draw and show you. So that the contact angle has to be measured from the fluid surface and not the other way around. So this is essentially the contact angle. So that means if we draw and complete this perpendicular, so that means for this fluid surface, right, there should be a force of surface tension in the upward direction that balances the gravity force. Let me just take this so we and draw it little more a broader version. So if this is the fluid surface, and so that means this is the contact angle that we are seeing, and we resolve this force. So this force is acting on this direction, and if this is resolved, right, so this is again theta. If this is resolved, this is F sigma in the vertical direction, which should balance the gravity force. So all we have to do is write the gravity force to be balanced on the F sigma, and note if this I take as a z direction, it should be the z component of the force. Now how to get the gravity force acting on this column of fluid? So that's basically the mass of the fluid times the acceleration field. The mass of the fluid on this column can be approximated using the dimensions of the height of the fluid and the diameter of the capillary. So it is primarily the density of the liquid times the volume of the liquid in this particular capillary times G. And the volume of the liquid can be written as the cross-sectional area times this height of this liquid in the column times G, and this can be written area, the cross-section area can be written as pi by 4 d square. D is primarily the diameter of the capillary column, and remember this is the height. Typically the height is taken as the height of the lower meniscus for the fluid, but nevertheless this is going to be very small, so one can even average it. Remember, there is always an engineering approximation given, so we want to find an approximate height at equilibrium when a fluid rises through a capillary. Now what about the surface tension force on the z-axis? So that means the vertical component. That's primarily the force of surface tension resolved on the cos theta, so which is primarily this this part, on the vertical direction, and the surface tension force actually acts on the circumference or the perimeter for creating this new surface, because a new surface is being created when a fluid rises through a capillary. So that means the perimeter, assuming that this is to be a circular cross section, we have it as a pi d. So this is sigma cos theta into pi d, and you can just balance it out, and you can see that this goes, so you can just exchange. Sorry, I think this I didn't complete. So pi by 4 d square h into g, this is on the gravity side. So this gives you the expression as h is equal to 4 sigma cos theta by rho g into d. So that means capillary rise, right, of a liquid in a tube of diameter d is given by h is equal to 4 sigma cos theta by rho gd. So this rho is primarily the liquid density, and this is the surface tension of the liquid, and this theta is the contact angle. Now one can arrive at an interesting observation from this expression. So let me just write an expression, 4 sigma cos theta by rho L GD. If theta is within 90 degrees, so if it is between 0 to 90, which is the case of a typical wetting fluid, right, you will have cos theta to be positive, so that means h will be a positive number, so which means the fluid will rise in a capillary tube. Now let's say if the theta is an obtuse angle, so suppose if it is greater than 90 and within 180, so this is typically the case of a non-wetting fluid, then cos theta is negative, which means h is negative. The understanding here is the fluid will not rise, the fluid will fall down in a capillary tube. So that means there will not be rise in a capillary tube, rather there will be a capillary depression. This is primarily the case when you have a fluid in contact with a material which it does not wet, right? So with this I end this video. What we have seen in this video is an expression for the capillary rise, the rise of a fluid in a capillary column, in a small column, with considering only two forces of gravity and the surface tension. We also saw why pressure force we have neglected. We arrived at a simple expression for the equilibrium height, and based on whether the fluid is wetting or non-wetting, the same expression represents either the rise of a fluid in a capillary column or the capillary depression. Thanks for watching this video.